Fourier series are important for a number of reasons. Amongst these reasons, Fourier series lead to a new perspective from which to view functions, known as frequency spectra. In this section, I'm going to introduce the notion of frequency spectra and explain how Fourier series naturally lead to this notion. Fourier series are particularly important because, amongst other things, they lead to the notion of frequency spectra. Think of a function. Essentially, a function embodies information of some sort. The traditional way to view this information is as being distributed with respect to time. In other words, the function is viewed as having a particular value at each point in time. Fourier series, however, provide a new way to view the information embodied by a function. Instead of viewing the function as having information distributed with respect to time, we can view the function as having information distributed with respect to frequency. In other words, the function is viewed as having a particular amount of information at each frequency. This distribution of information in a function over different frequencies is known as the frequency spectrum of a function. When a function is viewed in terms of its frequency spectrum, the domain of the function effectively becomes frequency instead of time. For this reason, this new perspective on functions is often referred to as the frequency domain, whereas the more traditional way of viewing functions is referred to as the time domain. And as we'll see shortly, Fourier series provide a means to quantify how much information a function has at various frequencies. In other words, Fourier series provide a way to define the frequency spectrum of a function. And as it turns out, many engineering problems can be solved much more easily when the problems are considered in terms of frequency spectra and the frequency domain perspective for functions. Before attempting to formally introduce frequency spectra, I'd like to consider a short thought experiment related to Fourier series. The goal of this thought experiment is to provide a better appreciation of the relative importance of the terms in a Fourier series. So consider the following problem. Suppose we're given the one periodic function x that has the Fourier series representation shown at the top of the slide. In other words, this Fourier series representation here, which if we plot it, the function looks like what's shown in the middle of the slide here. Clearly, this Fourier series has 8 non-zero terms, and suppose that we're asked to find the best possible approximation of the function x that is obtained by keeping only 4 out of 8 terms in the Fourier series. In other words, we wish to discard half of the terms in the Fourier series in a manner that incurs the least amount of error. How can we accomplish this? If we ignore the Fourier series coefficient in each term, in other words, focus just on the exponential part, in other words, the complex sinusoidal part, for example, the part I've highlighted here in the first term, and this part in the second term, and so on for the remaining terms, all of these exponentials would make similar contributions to the overall sum, because each of these exponentials have the same magnitude. They're all magnitude 1. If, however, we introduce Fourier series coefficients that are not necessarily all equal, so then we start introducing these constants like minus j over 10, minus 2j over 10, minus 4j over 10, and so on. Because these coefficients have different magnitudes, the overall contribution made by each of these terms will be different, because the overall magnitude of this term, for example, will differ significantly from the overall magnitude of this term due to the fact that the Fourier series coefficient in this term, this Fourier series coefficient here, has a much larger magnitude than this Fourier series coefficient here. So overall, the terms that will make the most significant contribution to the overall sum of the Fourier series will be the one whose Fourier series coefficients have the largest magnitude. Therefore, if we'd like the best approximation of the function x by using only 4 terms in the Fourier series, we should choose the 4 terms with the largest magnitude Fourier series coefficients, namely the terms with the coefficients minus 4j over 10, minus 13j over 10, plus 13j over 10, and 4j over 10. In contrast, if we wanted to make the worst possible choice, the worst choice that we could make would be to choose the 4 terms with the smallest magnitude Fourier series coefficients. In other words, the terms with the coefficients minus j over 10, minus 2j over 10, plus 2j over 10, and plus j over 10. And to better illustrate the consequences of making these choices, the approximations obtained with each of these 2 choices are shown plotted on the next slide. On the previous slide, we were considering an approximation problem where we wanted to obtain the best possible approximation of the periodic function x by keeping only 4 out of the 8 non-zero terms in the Fourier series representation of x. We concluded that the best choice was to keep the 4 terms with the largest magnitude Fourier series coefficients, and the worst choice would be to keep the 4 terms with the smallest magnitude non-zero Fourier series coefficients. Now on the current slide we have two figures that show the approximations of the function x obtained with each of these two choices. On the top half of the slide we have a figure showing the approximation of x that's obtained when the 4 terms with the largest magnitude Fourier series coefficients are chosen. So if we look at this figure more closely, the approximation is shown with the solid line, and the original function that we're trying to approximate, namely the function x, is shown with a dotted line. And if we compare these two plots, you can see that the approximation is a fairly good approximation of the original function. In other words, the solid line generally tracks the behavior of the original function x. Of course, there's a little bit of error, but generally the basic essence of the original function x is captured by the approximation. On the bottom half of the slide, we have a figure showing the approximation of x that's obtained when the 4 terms with the smallest magnitude non-zero Fourier series coefficients are chosen. And if we look at this figure in more detail, again, the solid line corresponds to our approximation and the dotted line corresponds to our original function x that we're trying to approximate. If we compare the dotted line and solid line functions in this graph, you'll notice that they're quite different. In other words, our approximation, the solid line function here, doesn't at all capture the general behavior of our original function x. In other words, the approximation that we have here is a very, very poor quality approximation. So the takeaway from this example is that the terms in a Fourier series with the largest magnitude Fourier series coefficients make the most significant contribution to the Fourier series summation. At this point, I'd like to show how Fourier series lead to the notion of frequency spectra. So for this purpose, it's helpful to write the Fourier series with the Fourier series coefficients expressed in polar form. So here we have a periodic function x that's expressed in terms of its Fourier series, which is this summation here. And what we're going to do is we're going to take the Fourier series coefficient ck and we're going to express it in polar form. So when we do this, what we can do is we can take the exponential that comes from writing ck in polar form and combine it with the exponential here that's already in the Fourier series in order to write the expression on the right-hand side here. And if we look at this right-hand side expression, in other words this summation here, each term is essentially a complex sinusoid, in other words a function that looks like e to the jk omega naught t, but because of this additional term here, the plus arg ck, the effect that this plus arg ck is going to have is it's going to take the complex sinusoid and shift it by an amount that depends on arg ck. So the physical significance of the argument of the Fourier series coefficients is they essentially apply time shifts to the complex sinusoids that are being added in a Fourier series summation. We also have this magnitude of ck appearing in the expression as well. The significance of the magnitude of the ck is that this is being used to apply an amplitude scaling to our complex sinusoid. So in effect what we have with the Fourier series is a whole bunch of complex sinusoids that are being shifted by various amounts that depend on the argument of the Fourier series coefficients, and then each of these complex sinusoids is then scaled by an amount, in particular amplitude scaled by an amount that depends on the magnitude of ck, and then we add all of these terms together. Now for a given k, in other words for a particular term in the Fourier series summation, the larger the magnitude of ck is, the larger the amplitude is of the corresponding complex sinusoid e to the jk omega naught t, and therefore the larger the contribution that the kth term in the Fourier series makes to the overall summation. Now because the kth term is associated with the frequency k omega naught, we can think of the magnitude of ck as telling us how dominant the frequency k omega naught is in the function x. In other words, we can use the magnitude of ck as a measure of how much information the function x has at the frequency k omega naught. So in summary, each Fourier series coefficient ck tells us how much the complex sinusoid at the frequency k omega naught contributes to the function x, as well as how this complex sinusoid is shifted relative to complex sinusoids at other frequencies. In other words, the Fourier series coefficients provide a way to view a periodic function x as consisting of information distributed across various frequencies, where the Fourier series coefficient ck measures the information in the function x at the frequency k omega naught. And this is essentially the notion of the frequency spectrum of a function. On this slide, I'd like to introduce some terminology related to Fourier series and frequency spectra, as well as make some additional comments on frequency spectra. So suppose that we have a periodic function x with fundamental frequency omega naught and the Fourier series coefficient sequence c. Then as a matter of terminology, the Fourier series coefficients, in other words the ck values, are referred to as the frequency spectrum of x. The magnitudes of the Fourier series coefficients, in other words the magnitude of the ck values, is referred to as the magnitude spectrum of x. And the argument of the Fourier series coefficients, in other words the argument of the ck values, is referred to as the phase spectrum of x. Now normally when we plot the frequency spectrum or magnitude spectrum or phase spectrum, we plot these quantities against the frequency k omega naught rather than versus k. And the reason for this is that k omega naught, which is a frequency, it has a physical meaning. It's the rate at which something's oscillating. Whereas k is just an integer index that's used to label a Fourier series coefficient. So it doesn't have any kind of concrete meaning. So this is the reason why we plot the spectra versus frequency rather than versus the integer index k. Since each complex sinusoid in a Fourier series has a frequency that is an integer multiple of omega naught, the spectrum of the periodic function x can only have information at certain specific frequencies, namely at frequencies that are integer multiples of omega naught. In other words, the frequency spectrum is discrete in the independent variable, which corresponds to frequency. Since the frequency spectrum is discrete in the independent variable, the plot of a frequency spectrum appears as a sequence of vertical lines. For this reason, this type of spectrum is sometimes referred to as a line spectrum. At this point, I'd like to consider an example to further illustrate some of the ideas that relate to frequency spectra, and in particular, I'd like to consider example 5.7. In this example, we're given a periodic square wave x that has the fundamental period capital T and the fundamental frequency omega naught, and the Fourier series coefficient sequence is given by ck, this formula here. And we're told that a is a positive constant, the a that appears in the formula right here. And what we're asked to do in this particular example is find and plot the magnitude and phase spectra of the function x, and also determine at what frequency or frequencies x has the most information. So first let's worry about finding the magnitude and phase spectra of x. So the first thing that we need to understand is what's meant by magnitude spectrum and phase spectrum. So the magnitude spectrum is simply the magnitude of the Fourier series coefficients. So in other words, what we want to compute is this quantity here. So we can find this simply by taking the magnitude of both sides of the equation that we're given for the Fourier series coefficients. So if we take the magnitude of both sides of this equation, this gives us this equation here. And we have two cases depending on whether k is even or odd. And the more tricky part to simplify is the k odd case, in other words, this formula here. So we can simplify this by making a few observations. So we're starting out with this expression here. We can use the fact that the magnitude of the quotient is equal to the quotient of the magnitudes to rewrite this expression in terms of the second expression here. Then what we can do next is we can observe that the magnitude of minus j2a is simply 2a, because we're told a is positive. And the magnitude of pi k is simply pi times the magnitude of k. So this is essentially what we have on this next line here for our odd k case. So that essentially gives us the magnitude spectrum, which we could then plot if we wanted to for various values of k. Then we go on to find the phase spectrum of x. So the phase spectrum of x is simply the argument to the Fourier series coefficients. In other words, what we're being asked to find is arg of ck. So all we need to do this is simply take the argument of both sides of this equation for ck. So if we do this, we get the first line here. And then we need to simplify each of these expressions for the k odd and k even cases. The k even case is easier to deal with. The arg of 0 is any real number. the answer is not uniquely determined, and in fact any real number would satisfy this. This would be a correct answer to arg of 0. But let's choose a sensible one. Let's pick a nice number, 0. So we've chosen 0 here. And then we need to simplify this arg of minus j2a over pi k, in other words, the k odd case. So essentially what we have in this case is this expression here, where the quantity in round brackets, the minus 2a over pi k, is a real number because a is a real value and k is an integer. Therefore, the quantity in square brackets, j times a real number, is a purely imaginary value. So overall what we have is something that looks like the argument of a purely imaginary number. So no matter what k is, we're always going to be somewhere on the imaginary axis because the number that we're dealing with is purely imaginary, which means the argument of this complex number, there's only two possibilities for this. It could either be plus pi by 2 because it's on the positive part of the imaginary axis, or it could be minus pi by 2 because it's on the negative part of the imaginary axis. So we just have to figure out under what circumstances it's on the positive part of the imaginary axis and on what circumstances it's on the negative part of the axis. So you can see here with the expression that we're dealing with, if k is less than 0, then the quantity in round brackets here will be positive. In other words, we'll have j times a positive number, which is somewhere on the positive part of the axis, which will give us pi by 2 for the angle. So this is the reason why when k is less than 0, we get a value of pi by 2 for the angle. On the other hand, if k is greater than 0 in this formula here, this means that we'll have j times a negative value, which means that we're somewhere down on the negative part of the imaginary axis here, which means that the argument associated with this complex number will be minus pi by 2. In other words, this angle here. So this is where this minus pi by 2 comes from. Now at this point we can use a clever trick to collapse these two cases for k odd into a single case, and the observation we can make is the only difference between this first case and the second case here is a sign difference. One of them has a minus sign thrown in here. And the sign difference depends on whether k is positive or negative. So what we can do is we can collapse these two cases together by simply using the signum function and writing this as minus pi by 2 signum of k. And in case you might have forgotten, the signum function is defined in this way. It's the arithmetic sign. So if you plug into the signum function a positive value, you get plus 1. If you plug in a negative value, you get minus 1. If you plug in 0, you get 0. So it's essentially the arithmetic sign. So with that in mind, we can collapse these two cases here together for k odd into this single case. And now we have the phase spectrum. And of course, now that we have this formula for the arg of ck, we can substitute in various values of k and generate a plot of the phase spectrum. In the last part of the example, we're asked to determine at what frequency or frequencies x has the most information. So to deduce this, we need to use the magnitude spectrum. And in particular, what we're interested in is the frequency at which the magnitude spectrum achieves its maximum value. So the magnitude spectrum is just the magnitude of the ck values. So if we look at the expression that we got for the magnitude of the ck values on the right-hand side here, you'll see that this function is going to take on a maximum when k is either plus or minus 1. So when k is plus or minus 1, the magnitude spectrum is going to have its largest value, and this corresponds to the frequencies minus omega naught and plus omega naught. So the function x has the most information at the frequencies plus omega naught and minus omega naught. In this example, in addition to finding the magnitude and phase spectra of x, we're also asked to plot these spectra as well. So we're going to take the formula that we got for the magnitude spectrum, this expression here, and the formula that we got for the phase spectrum, this expression here, and we're going to plot them. And I'm going to show you on the next page the result that we get when we plot these functions. Now we're looking at the next page of the solution, which includes the plots of the magnitude and phase spectra. I just want to note that when we plot the magnitude and phase spectra, you'll notice that we label the horizontal axis with frequency rather than with k values, in other words, rather than with the Fourier series coefficient indexes. Just as extra annotations, I've labeled the k values that correspond to the different frequencies, but normally we wouldn't include this in the graph. And a similar comment applies for the phase spectrum. I've added as extra annotations the k values that correspond to the different frequencies, but normally we wouldn't include this. If we look at the magnitude spectrum, we can see quite clearly that the frequencies at which the function x has the most information, in other words, the places where the magnitude CK, in other words the magnitude spectrum, achieves a maximum is at the frequencies minus omega naught and plus omega naught. So these are the frequencies at which X has the most information. Also, we can make another observation, which is that the magnitude spectrum is even and the phase spectrum is odd. And this is not by coincidence. This is due to the fact that the function X is real. And if you recall, a real function will always have Fourier series coefficients that have conjugate symmetry. And one of the consequences of this is that the magnitude of the Fourier series coefficients will be even and the argument of the Fourier series coefficients will be odd. At this point, I just want to make a few comments about frequency spectra of real-valued functions. So recall from earlier, if we have a real-valued function x, and we find the Fourier series coefficient sequence c for this particular function, the Fourier series coefficient sequence will satisfy a relationship of this form. In other words, the coefficient sequence c will be conjugate symmetric. And if we take the magnitude of both sides of this equation, this gives us this equation here. And if we take the argument of both sides of this equation, this gives us this equation here. And if we look at each of these two equations that we have that involve the magnitude and the argument of the CK values, what we can infer from this is the magnitude spectrum of a real function is always even due to this particular relationship here, and that the phase spectrum of a real valued function is always odd due to this relationship here. Now, since real valued functions have symmetry in their frequency spectra, we typically ignore negative frequencies when we're dealing with such functions. Essentially, what happens in the case of real valued functions is that the portion of the frequency spectra for negative frequencies is completely redundant. It doesn't contain any information that can't be inferred from the portion of the frequency spectra for non-negative frequencies. So for this reason, we often ignore negative frequencies when we're dealing with real valued functions. This said, however, the negative frequencies can become important, and in particular, they become important in the case of dealing with complex valued functions that are not real valued. In the case of complex valued functions that are not real valued, the frequency spectra no longer possess symmetry, and therefore the negative frequencies become quite important.